to yet another class of ML-Dawn. So, previously we talked about maximum likelihood estimation and we derived the formulas, and particularly one particular formula actually that described the whole maximum likelihood estimation's goal. And we explained why maximizing the likelihood is equivalent to minimizing the error function that we described previously. Right, so today I'm going to show you how you can use maximum likelihood estimation to address real-world problems. In particular, regression is the one that we're going to talk about today. So the idea is that we will use maximum likelihood estimation to derive the appropriate error function that would suit our needs to solve a regression problem. So let's first do a simple recap on two of the ideas in this whole lecture today, and then I'm going to jump into what I've promised to do in today's class. So just a fast recap on maximum likelihood estimation first, just to give you a little bit of review as to what we talked about the last class. So the main idea behind maximum likelihood estimation is that we said that the error function that we're going to use is equal to minus the log of our likelihood, and the likelihood is the probability of our observations given our model, right? So basically maximum likelihood estimation means that if I can maximize this guy, so if I maximize this guy, then it means that this whole thing will get minimized, right? So it means that the whole error would get minimized, and the whole reason is because of this little minus here that we got. And that is common practice in machine learning. They usually come up with this the idea of likelihood, and then they would put a minus there because we are used to minimizing errors. That's the only reason that we got the minus over there. And yeah, so if you remember, we said that the observation D is nothing but some pairs of data. In particular, it means the inputs, let's show them with D to be consistent with our previous lectures, and our target value, the ground truth, right? The thing that we're actually trying to predict, right? So if I substitute this with these D and T with D in my formula, and if I remember, I said that M, or our model, is nothing but the weights in my neural network, right? So we are assuming that we have a neural network here, right? So everything that I'm going to talk about, the whole error functions that we're going to generate, they will all be basically applicable to a neural network. And they can be applicable to other machine learning algorithms as well, but we are going to focus on artificial neural networks, basically. Now, if I want to substitute D and M with their equals, what I'm going to get is, so I'm just going to forget about the minus log part here, and just to make it mathematically more convenient, if I say that, so the probability of my observation, which is nothing but D and T. Remember, D is a vector, T is a vector, so D is a bunch of numbers that would be the inputs to my neural network, and T is another bunch of numbers that are basically the ground truth, the thing that we're trying to predict. Remember, I'm saying numbers, right? But they can be also vectors. But I'm just trying to simplify this, okay? Because that is not the main focus here. So so the model is nothing but the weights that I have here, right? So this is the whole idea. So this again is my likelihood. Nothing new yet, right? So then I can expand this, right? So this guy right here, I'm going to put a star here, and I'm going to continue here, right? this guy right here, this likelihood equals the following. So if I have a conjunction of two variables conditioned over another, so in this case d and t conditioned over w, mathematically I can expand this whole thing and I can say that this equals the probability of my ground truth, right, given my input and my weights or my parameters, right, multiplied by the probability of my inputs given my w. So that w is basically expanded, kind of shared by the two terms here, right? And then one thing to remember here is that this guy right here, you see, d and w are independent. So if I say, like, what is the probability of d conditioned over w, meaning that d, if we assume that w has already happened, this is exactly equal to saying that so substituting with the probability of d. So w can be cancelled out because they're independent. So this whole thing would be equal to the probability of t given d and w, right, and multiplied by the probability of my observation, d, right? So just in short, I can say that error equals minus the log of probability of t given d and w multiplied by probability of d, right? So far so good. Now, if I want to basically distribute the log among the two terms, if you remember, the log of a multiplication is the sum of the logs of each one of the terms. So basically, if I keep the minus out, I would have the log of probability of target value given my observation and w plus the log of the probability of my observation, right? Now, remember, what I'm doing here is maximization, right? What does that really mean? The only thing that is happening here is that I'm going to learn a model to do a certain task, right? I'm going to minimize an error function. How am I going to do that? I'm going to adapt my model, right? I'm going to let it mutate and basically change its parameters over and over until the outputs of the model is so close to the ground truth t, right? So the only knobs that I have at my disposal to play with my model are the w's, or the parameters of my model, right? The weights of my neural network, right? So I'm going to maximize this whole formula with respect to my w, okay? So because I'm going to do that, the terms that have nothing to do with the w can get cancelled out during my maximization, right? Because I'm going to do partial derivative, I'm going to play with that in the future. Well, I'm going to dig into detail later on, but so far, I know that this term right here is independent of my w, or the parameters of my network, right? So basically what I will end up with, let's use another color, a little bit more fancy. The error is nothing but minus log of the probability of my target values given my observation and w. Sorry, small d is basically my input. Sorry, I think I basically said it wrong a couple of times. So the small d is my input. Okay, sorry about that. Right. So this is my error function, right? The goal is to minimize this, or to maximize the probability of target value given my d and w, right? Remember, what I'm doing is I want to maximize the likelihood or this probability in the log right here. It means that I want to come up with a model with a set of W's that if I have my input D, I'm gonna maximize observing my target values. I'm gonna come up with a set of weights with a model so good that I'm maximizing observing the target values, the ground truth, right? So the output of my network would be so close to what they should be. So that's the whole idea. If I have that type of model that would maximize this probability, it means that I've already minimized my error. And that is the whole idea behind maximum likelihood estimation. Right, so the second thing that I want to have a fast recap on is the regression problem on its own. So imagine that I have a simple regression problem where we have two axes, right? Let's say one axis refers to the engine capacity of a car, and the other one is the price, right? So imagine that you have gathered some real life data, and what you've come up with is that it's a set of numbers, right? So say this is the way it is going up, right? So this is the real thing, right? This is the real numbers, right? And you want to use this as a training data for your machine learning algorithm to learn how to predict your price, the price of the car, given the input, which is the engine capacity. Excuse me. Right? So imagine that your model has, well, during training, say this is the first round of training, and your model has predicted, let me choose a better color here, let's go with green, right? Let's say that your model has predicted values like this, right? So say the first one is here, second one is here, and the third one it is here, and fourth one it is, say, here. Basically a kind of a very reversed, basically, of what is actually happening here, right? So it means that given the engine capacity of like this much, like this many liters, instead of predicting this much, like this many dollars, you predicted this much dollars for your car, right? So this means that your model is doing a horrible job, right? So you have to come up with a way to tell the model that, okay, this is how much you have screwed up, right? And then you would ask your model to tune its parameters, which is the weights of your model in an artificial neural network, in a way that it would minimize that screw up. So the screw up is nothing but the error, right? So you want to minimize an error, which is the same as maximizing the likelihood of observing these red crosses here, right? Observing the real value of the car, right? So what you need, this is very important actually, please pay attention to this part. What you need is a measure of distance. Between what? What and what, basically? Between the ground truth, hence the red crosses, and the output of your network, say, let's call it y, right? You want to find the gap between these two, and you want to minimize this distance. My friends, this is nothing different than saying that I want to maximize the likelihood of what? Of the ground truth, right? So minimizing this distance should equal to maximizing the likelihood of observing the truth. So I would tune my model in a way that it would generate the output, the ground truth, right? So how does it really work? So you need a measure of distance, right? So let's consider this part right here. let's consider the first column right here and think about the way we can measure the difference between the prediction and the ground truth. So basically the way it works is that if we assume a Gaussian function here, right? So by that I mean a Gaussian function that is centered around your prediction. That's right, your prediction, not the ground truth, but the prediction. So that would mean that I'm going to have a function like this one, right? If it's centered around something like this, right? Cool. Now, here's a question. How likely is that? So just ignore everything else in this figure and just look at this Gaussian, right? How likely is that this red cross over here has been generated by this Gaussian? I mean, if I were to sample from this Gaussian, right? How likely is that I will generate a value over here, which is the red cross? So a price over here, basically. If it's a Gaussian that describes the distribution of the car prices for this engine capacity. Please pay attention to the way I use these terminologies, the way I talk about this. This succession of words basically. It's very descriptive of what's the soul of this whole lecture here, right? So given this particular engine capacity, if I assume that this green Gaussian is explaining the distribution of the prices for cars that have this engine capacity, how likely is that the ground truth price, I mean the actual price, which is this guy, could be sampled, could be generated by this Gaussian? How do we measure that, right? So if I were to transfer this whole thing in a simpler, like kind of a horizontal view, right? You have a Gaussian like this, right? And this is the center of the Gaussian, right? And you have a value here, right? So if I were to, so basically this thing, this axis is well, maybe I should use a different color. So basically this axis is the price. So I'm just transforming the whole figure to make it, well, more understandable, right? If I asked you, how likely is that the actual price, or my ground truth T, has been sampled from my model, so how likely is that? Basically, how likely this probability, how likely is that my ground truth has been generated by this Gaussian, given, please pay attention, this is very important, given my input, which is this particular capacity here. Given my input, so say D1, right? Say, let's call it T1, right? It's T1, right? Given my input, my first input, and let's call it W1, right? It's all the weights in my neural network, right? So given these guys, right, how likely is that this particular ground truth could be generated by my network, right? So I have to assume a distribution on this probability to be able to come up with a number, with an actual number, right? So the way it works is that so I said that we're going to use a measure of distance, right? The way I'm going to measure the distance, or the likelihood of T1 having been generated by this green Gaussian, is that I'm going to put T1, this particular value, in the formula of my Gaussian. Now, what is the formula of my Gaussian? So let's write it with a green pen. So the formula of a Gaussian is quite simple. It is 1 over square root of 2 pi the standard deviation of Gaussian and the exponentiation of minus, right, here I would say the T1, right, that is the data that I have, that is the ground truth that I want to generate, minus y1. What is y1? y1 is this guy right here, because that is what I've predicted, right? The square is what I've predicted. Squared divided by 2 times standard deviation squared. Please pay attention what we're doing here. This is the Gaussian, right? So if I were to tell you that I can use this Gaussian to tell you how much I've screwed up, like that I can use that to measure the distance between T1, in this case T1 and Y1, right? It's like Y1 is what I've predicted and T1 is what I should have predicted, right? I can tell you that if I put T1 into this formula, I will get a number. What is this formula exactly? It says that for a variable, say T1 here, I have a Gaussian, right? Its center or its mean is Y1, and hence I put Y1 here, right? And I've got the standard deviation over here as well. Now, please pay attention to that. The farther Y1 and T1 are from each other, the more this whole formula will get, right? Sorry, my apologies. The farther the T1 and Y1 get from each other, the lower this formula will get. What does it really mean intuitively? You see, if I continue this Gaussian, it eventually leans towards 0, right? So if I were to put the particular value of T1 into this formula, I would get a very low value here, right? It means that it's very highly unlikely for this Gaussian to be able to generate the T1 value for me, right? Now, if I had a Gaussian sent kind of closer, maybe around here, I would say, okay, this is touching the Gaussian around here. Now, if the Gaussian was here, now it will touch the Gaussian around here. So it is in the more likely area, the higher, the area of the likelihood with much higher probabilities, right? And then I can say that this Gaussian is highly generate values very close to T1. Actually, T1 is kind of the center or the mean of the Gaussian, and that means that it's in the region of the Gaussian that is very probable for the numbers around T1 and T1 included to be generated by this Gaussian, right? So as you can see, I can use the Gaussian to basically explain the difference between my ground truth and my prediction, right? Let's erase this whole thing, right? So that is the whole idea behind basically regression and how we can basically what the goal is in regression, right? So what is the idea here? I will use that likelihood. I will measure and basically use the output of my Gaussian, right? And then I'll try to change the parameters of my model or the W's in a way that this Gaussian would get closer and closer to the ground truth, right? So currently, if I were to use a line to describe my predictions, this line would go something around like this, right? Whereas the ground truth has a positive trend. Let's use a direct line, right? Now, if I were to reduce this distance, say for the first prediction and the first ground truth, which is this one, then the prediction would later on fall very close to my ground truth around here, right? and then the next prediction would be, say, here, and say the next prediction right around here, and then next one very close to here, right? So then if I were to use, if I were to fit a line to this, it would be kind of similar to a line like this. You see, it is far better than this previous one that was going downwards. It was horrible. Now the predictions, these green squares, are much closer to the ground truth, these red crosses here, right? So again, if I were to, let me kind of declutter the figure. Cool. So now, as you can see, that the difference between my prediction and my ground truth is far smaller, right? So if I were to consider a Gaussian centered around my prediction, I would get something like this, right? A Gaussian like this, right? Now, if I were to measure the likelihood of observing the ground truth, this red cross, by the green Gaussian, I would get a much higher number because of, let me again describe this graphically. So if this is my Gaussian, right, and say this is my y1, or the square, the center, and say the ground truth is now much closer, which is, say, t1, right? If I were to well, use axes here. Oh, sorry. Let me use the white, right? White color. So if this is y, right? And so this right here would tell me about the likelihood, right? Likelihood of what? Likelihood of observing t1 by this Gaussian, right? If this Gaussian were to explain my ground truth. So if I were to put t1, this particular value of my car price, right? So this is the price, right? Into the formula of my Gaussian, I will get a number, which is nothing but exactly, so basically I will put this t1 into the formula, and what I will get, this would be the output, right? This is the output, which is much closer to the previous case where the ground truth was far away, kind of here, right? And so what I mean is, well, the ground truth has always been there, but my point is, if the ground truth was much far away from my prediction, and if I were to measure the likelihood of that ground truth having been generated by this Gaussian, I would have gotten a number kind of very close here, right? Very close to here. So for this particular, if this was my ground truth, if this was my t1, and I were to claim that this is the Gaussian, this is the so this is what's going to well, generate this ground truth, I would get a much lower number. You see, there's a very big gap here, right? So, but now I have learned better, right? And now this Gaussian over here, this is far more likely to generate my t1. So the likelihood of observing t1 given my input and the parameters of my model is now much higher compared to the previous case where I had a very bad estimation of the ground truth and I had a downward going line for my predictions. Right, this is very exciting actually. It took me a long time to figure all this out when I first started reading about these, so I really wanted to learn it very deeply, and well, I think I got it now. It's been nearly 2.5 years that I've been involved with machine learning. Anyways, so what I said the very first was that I'm just going to write this over here. The error that we're trying to minimize is minus the log of the likelihood, right? The probability of the likelihood of my target values, the probability of t given my inputs d and the weights or the parameters of my model. Let's remember this, okay? Now, I said that I'm going to assume a distribution of the likelihood, right? For regression, I'm going to consider a Gaussian distribution because Gaussian just reduces from both sides. It goes down symmetrically from both sides. So the farther away a point is from the center of the Gaussian, the farther it gets, the likelihood of that point having been generated by that Gaussian would get symmetrically lower and lower from both sides. So it's basically neutral towards which side you're talking about. Doesn't matter from which side that the ground truth is getting closer to the center of my Gaussian or is getting farther away. If it gets farther away, the likelihood of observing that ground truth would get lower and lower symmetrically from both sides. Lovely. Now, so let's remember this formula right here. Let's just keep it over there. And now I'm going to say that, okay, I'm going to assume the Gaussian distribution for my likelihood, right? Now, remember that by maximizing that likelihood, I'm gonna minimize my error. So by maximizing the likelihood, I mean that I'm gonna estimate a better and better and better center for my Gaussian. I'm gonna shift it more and more towards the ground truth to maximize the likelihood of observing t, hence minimizing my error, right? So remember that if I have a bunch of ground truth, right? So again, this is the example that I had here. And if I had a bunch of ground truths, right? Ground truth points like that, right? And if for each one of them I were to, and say again, I have some predictions, right? So one prediction here, one prediction here, one here, one here, oh, you get the story, one here, right? Now, for every ground truth, I have a prediction, right? So I have pairs here, 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 and here, right? So for every one of them, I'm gonna have to consider this Gaussian. So this Gaussian would be here, this Gaussian would be here, the other one would be here, the other one would be here, and the other one would be here, right? Sorry, oh, that was horrible. Right, the other one would be here, right? What I'm trying to do is that measure the gap between each one of these pairs, right? So for each ground truth, how much have I screwed up? And I want to minimize that, right? So basically, I want to maximize, please pay attention, the likelihood of observing each one of these ground truths by their corresponding assumed Gaussians, which are this guy, this guy, this guy, this guy, and this guy, right? So if I assume that the probability of observing my ground truths, remember that t is a vector of numbers, so t includes all these red crosses, all these prices, the true prices for their corresponding capacity, engine capacity, which is, well, this guy right here, right? Remember, this is the engine capacity, and this is the car price, right? So if I were to assume that the probability of observing each one of these guys, each one of the ground truths, right? T has all these ground truths inside of it. It's a vector, right? Given my inputs, right? So all these engine capacities and the parameters of my model, the weights, if I assume that each one of these guys are distributed normally, right? The idea is that I want to shift these Gaussians in a way that would maximize the probability of them generating my ground truth, right? So what does it really mean? It simply means that, so the best case for each one of these Gaussians is to shift so much that, for instance, for this case, the center of my Gaussian would overlap with the ground truth. So basically, I want the center of my Gaussian to be as close as possible to my ground truth. What does it mean? It means that the ground truth would fall right in the middle or very close to the middle of my Gaussian. This means that it would nearly maximize generating that particular value, that ground truth, by that Gaussian. It is the optimal Gaussian that is very probable for that to generate that ground truth, right? So if I assume that the ground truth has a normal distribution, which is the case in our assumption here, the idea is that I want to estimate the center or the mean of that Gaussian, right? I want to basically find a mean, find the center, the best centers or the best Gaussian, right? By changing the center of the Gaussian and basically changing the whole, basically shifting the Gaussian up and down, right? I want to find the best position or the best center for the Gaussian. Where is the best center? It is exactly where the ground truth is. So basically, I want to make the prediction and the ground truth as close as possible to each other. That's the whole idea, right? Now, remember that my ground truth is indeed the ground truths, basically, if they are the class labels, or in this case, which are real numbers, right? They're prices. One could be $12, one could be $15, 12.5, whatever. They're independent of each other, right? So the likelihood of observing the first ground truth by this Gaussian, the second ground truth by this Gaussian, the third ground truth by this Gaussian, the likelihood of observing each one of them is absolutely independent of each other. They have nothing to do with each other. Because of that, the likelihood of observing all of these ground truths by their corresponding Gaussians is equal to the multiplication of the individual likelihoods of these ground truths. It means that, so say I have, so let's say K is the number of my ground truth. Say values, basically t's, right? The number of t's that I have, right? So if I want to measure the likelihood, so basically if I want to measure the overall likelihood of observing all these ground truths, pay attention, all of the ground truths, I will calculate the likelihood of observing each one of those likelihoods separately, right? Those likelihood numbers separately, and it will multiply them together. Why? Because they're independent. You remember that in probability, if I were to say, what is the probability of observing A and B, and if I had told you that A and B are independent, you would say that is equal to probability of observing A multiplied by probability of observing B, okay? Because they're independent. So that's the story again here. So if I were to tell you that what is the probability of observing target value 1 or the ground truth 1, and the probability of observing ground truth 2, and the probability of observing ground truth 3, blah blah blah, until the probability of observing ground truth K, which is the end of the line, given all my inputs, which is D1, D2, D3 until DK. I'm not going to write all that here, and all the parameters of my model. You could have thousands of weights in your neural network. So this is exactly equal to probability of T1 given DNW, pay attention, multiplied by probability of T2 given my inputs and my weights, all the way multiplied by the probability of Tk given my inputs and my weights, right? Because they're independent of each other. So basically I'm going to calculate the likelihood of each one of these ground truths and multiply all of them together, right? Now, if I could maximize that total, that the result of that multiplication, it means that I will have each one of those Gaussians has gotten as close as possible to my ground truth. So basically, I have found the means or the centers, the optimal centers of each one of those Gaussians, because it's in a way that the multiplication of the likelihoods of all my ground truths has gotten maximized, right? So if I want to calculate this probability here, I'm going to write it down here, right? I'm going to have a multiplication, so I'm going to use a symbol here, a multiplication, for all my ground truths. So I have, say, j equal 1 to k, which is the number of my ground truths, right? And then the formula of my Gaussian, right? Again, I have 2 pi here. I have a standard deviation j. Why? Because each one of these Gaussians has its own standard deviation, or it's spread by how wide or how narrow it is, multiplied by the exponential of, and this is what we have in the power, that particular ground truth, t of j, so in this case, say the first one, minus my prediction for that tj, which is yj squared, right? So this is kind of finding the difference between my prediction and the ground truth, right? And remember, yj here is the center of this particular Gaussian, the jth Gaussian, right? So if they get absolutely close to each other, tj and yj, basically I have shifted the center of my Gaussian, which is the yj, which is my prediction, so much that it has gotten so close to my ground truth of tj. What does it really mean? It means I'm actually predicting a value very, very close to my ground truth. That is fantastic. It means that I'm predicting the actual thing that I'm looking for. That is the ultimate goal, basically. My machine learning algorithm has gotten super smart. And the denominator has 2 of the standard deviation of the jth Gaussian squared, or variance of it. So remember this. This is key. This is absolutely important. This is the whole story. This is the whole story for a regression problem. Remember how we got here. The goal is to minimize my error function over here. So I have a probability here. So I assumed an appropriate distribution for my target values here. So the likelihood of my target values. I assumed a Gaussian distribution, and since my target values are dependent of each other, the total likelihood of observing all of the target values equals the multiplication of the likelihood of observing each one of my target values or my ground truth values. Right, so let's work at this problem, right? So now I have the formula for my likelihood. Now I'm gonna put it into my error function, which is minus the log of my likelihood. And I want to see what I'm gonna come up with eventually, right? I'm gonna maximize this likelihood, and eventually I'm gonna minimize that error during the training of my neural network. So the training is not the focus of my work, but I'm just gonna find that final error function for a regression problem, right? So error equals minus the log of, so instead of probability of t given d and w, I'm going to put formula number 2 over here that I've basically come up with in the last slide. So the log of this guy, the log of multiplication, j equals 1 to k, of all these guys over here. Right? I don't want to write it over here again, because there's a point here. Remember that the log of a multiplication would be the sum of the logs. Remember that the log of a multiplied by b equals log of a plus log of b, right? So this log will be distributed inside this multiplication, right? So eventually this would be that the error would be equal to the log would jump in. So I'm going to keep the minus here. I'm not going to touch that. So the multiplication would turn into a sigma, a sum. Again, j equals 1 till k, the number of my ground truth. And then I'm going to have the log of this whole thing, right? I'm going to write it this time because I'm going to need it. So what is the denominator here? Or let me just write the whole thing right here. So basically that would be 2 pi integration j by dA minus tj minus yj in parenthesis squared 2j squared. Yeah, that's it. Right. Now, again, the error would be equal to minus sigma, right? J equals 1 to k, right? Now, remember, again, we have a multiplication. So, again, this is the first term, and this is the second term, right? So I can distribute log into that. Remember that when I say log, in this whole story, the base of log is the famous number e, right? Or the natural logarithm, or the ln, right? So the ln of the exponential of, say, to power a, whatever it is. So ln has the base of e, right? So these guys cancel out each other and we will end up with a. So the power would basically shift here, and I'm going to have basically a multiplied by ln of a number, which is e in this case, with the base, and the base of the logarithm is e in this case. So this guy right here would be equal to 1, and that is why I end up with a in the first place. So now I'm gonna distribute the log inside, right? So this would be the log of the first term, which is the log of 1 over square root of 2 pi sigma j plus the log of e to the power minus tj minus yj squared 2 sigma j squared, right? Now, now again, this can get simplified again. This is and this is actually quite fun because, well, this is math and it has no exception. You can just work it out, and you I promise you we're going to get to a very interesting function at the end. So the log of 1 over this whole thing, right? What does it really mean? It means that I can simplify it very interestingly, actually. So remember that the log of say a divided by b equals log of a minus the log of b, right? So again, we have a division. A is number 1 and b, the denominator, is this guy right here, right? So this would be the log of 1, which is 0. Log of 1 to any base of the logarithm would be 0, minus the log of the denominator, which is the log of this whole thing, 2 pi j, right? So, and this would be plus, so remember again, log of e to the power of something, whatever it is. Since the whole log, and I mean the log in this whole story that I've been talking about is the natural log, right? So the base is e, right? So since the base is e, then the log of e to the power of something, when the base of the log is e, you can just switch that to the whole power, the power of the exponential here, right? So minus tj minus yj squared divided by 2 sigma squared would be the result of this whole thing, right? So this would be plus the whole thing, right? So this would be the so basically minus, how am I supposed to put this right? minus tj minus yj squared 2 sigma j squared, right? Now, obviously, plus and minus here would just cancel out. And what we will end up here would be, so the error would be minus, again, the sigma, j equals 1 to k, multiplied by, now, let's do something here. Let's do something interesting. So that would be minus, let's say that, okay, let's consider these two, the square root of these two, right? I mean 2 pi sigma j squared. What happened? I basically raised the whole thing to power 2, right? So square root disappeared and sigma j turned to sigma j squared. Because I've done that, I have to add a 1 over 2 here to cancel that effect, right? Because, well, the log of a, right, you can say it equals to 1 over 2 the log of a squared, right? Because 2 would come down and cancel out with 1 over 2, and you will end up with log of a again. So it's a simple math trick, nothing crazy here. And then I'm going to have the minus here of tj minus yj squared divided by 2 sigma j squared. Lovely. Right. So I cleaned it up a little bit. Now, again, I can simplify this again. So again, we have a log of a multiplication here, right? So let's continue. So error equals the minus of sigma, again, j from 1 to k. I'm not going to write it again. So this will be 1 over 2 by log of 2 pi, again 1 minus 1 over 2 the log of sigma j squared. So, and the last term would remain intact. So tj minus yj squared 2 sigma j squared. Right. Now, one thing to remember is that this guy right here is a constant, right? So during my, basically my maximization, it has no effect, it's a constant value. So during my maximization of my likelihood or minimization of my error, I can ignore that basically, right? So I'm just gonna say that, okay, this term can be ignored during maximization, and I will end up with the final error function over here. So again, you see minus 1 over 2 and minus 1 over 2 here, they can get out of this whole thing, and that they will be multiplied by this minus over here, right? So I can just factor them out, and minuses will disappear, and I will end up with a 1 over 2 outside here. The sigma will stay, again j equals 1 from 1 to k, and I will end up with tj minus yj squared divided by 2 sigma j squared plus the log of sigma j squared. Now, to those of you who are familiar with neural networks, with machine learning, you know that we have a very famous function called the sum squared error function, right? I'm just going to write it here as a side note, the sum squared error function, right? What is that? It's very famous actually. It's 1 over 2 multiplied by the sigma of the differences between my ground truth and my prediction, right? So what it is basically very simple here. Oh, sorry, oops, I made a mistake here. I hope that you've seen it. So 1 over 2 here, I've already filtered it out. I basically cleaned it out because, well, I factored 1 over 2 and I got it out of the whole brackets. So this is what I'm going to end up with eventually, right? Now, back to my point. So the sum squared error, right, is 1 over 2 multiplied by the sum of the differences between my ground truth, say Tj, and my Yj, or my prediction, squared. This is the sum squared error, a very famous error function in machine learning, actually. Now, as you can see, I have the 1 over 2 here, I have the sigma here, I have Tj minus Yj here, I have the squared here, but I have 2 terms extra here. What are these? What is sigma j again? What is sigma j? That is the standard deviation of the jth Gaussian, right? Now, what they don't tell you is that in the literature, in sum squared error, they assume that all the Gaussians that I showed you, I think over here, yes, each one of them has the standard deviation of 1. So so the sigma of j for each one of them equals 1. So they consider it to be constant. So the only thing that they're going to play with is the center of the Gaussian, just by shifting it up and down, right? So to find the best Gaussian that would describe the ground truth. So if I do that, if I consider a standard deviation of 1 for each one of these Gaussians, what I'm going to end up with is that this denominator would be 1 squared, or would be 1, and this right here would be the log of 1 squared, which is 1 again. The log of 1 is always 0, and the denominator of 1, well, we can just ignore that, because anything divided by 1 is itself. So what I'm going to end up with eventually, if I consider sigma j equals 1 for all j, which is basically 1, 2 until the kth j, if I consider that sigma j is 1 for all of them, what I'm going to end up with is quite interesting, actually. So E would be 1 over 2 multiplied by sigma of j equals 1 to k of the ground truth j minus the prediction j squared. Now that, my friends, is the famous sum squared error function that everybody keeps talking about. Whenever they come up with a regression problem, they talk about the sum squared error function, and this is how you get it. So remember, what is so important here is this. So minimizing, so let's just say maximizing the likelihood t given the input and w, this equals minimizing my error, and all of that equals to minimizing my sum squared error. So remember, this is how the likelihood relates to the sum squared error for a regression problem, right? Remember that by minimizing this error function right here, the sum squared error function, I will find the best sets of Gaussians, basically the best centers for those Gaussians that are so close to my ground truth that I would end up with basically a line, or if I want to basically plot a line that is, so this dashed line over here, a line that is very much close to the ground truth line. And if I can keep training the model over and over using the error function, using the training techniques in, say, my neural network, let's say like backpropagation, to minimize the sum squared error, I will end up with a line that is very, very close to this red line over here. So I'm going to do a great job describing my ground truth values. So, the morals of the story. Now, for regression, if we assume that our likelihoods, let's switch to white, our likelihoods, given D and W, are normally distributed, let's show it with normal, with, say, a mean and a variance, right? If I assume that, and then the associated likelihood, it just looks like the squared error or the sum squared error function. So this is the moral of the story. This is how they're very close to each other. They're very related to each other, right? So basically, this means that minimizing the squared error really means doing the maximum likelihood estimation, right? We have something here that I probably haven't explicitly talked about, and that is the linear case over here. What does it really mean? So if you have an artificial neural network, right? It has an input, it has an output, right? Remember, what I'm gonna predict are, remember, the centers and well, let's just make it simpler. The centers of my Gaussians, or the parameters of my Gaussians, right? So this means that the predicted value is, let's say, member of the real numbers. It's a real number, right? So because of that, because of this whole story, the output layer of my artificial neural network is considered to be, remember, linear. This is very important for regression. Why? Because I don't want to apply any transformation in the output of my artificial neural network. Remember, I don't want to generate probabilities. I don't want to generate class labels. I want to generate a real number. So I'm not going to do any kind of transformation on my output. I want to just generate raw, real valued outputs, right? Which are in this case, are the centers of my Gaussians, which ideally will overlap with my ground truth, and we get so close to the ground truth that would minimize the sum squared error, or the sum of the differences between the ground truths and my predictions. Whew, that was a long lecture, but I hope that has been informative for you. So this is the whole idea. We have the error function, basically. The error is minus the log of the likelihood, right? And then for different types of problems, we focus on different types of distributions of our error function. For regression, we consider the Gaussian distribution, and we try to output the parameters of our Gaussian. So in a simplified case, we will generate only the means or the centers of the Gaussian. And if we want to get more technical, we can also generate the standard deviations of all the Gaussians. Right, so basically we are trying to generate the parameters of our distribution, of our Gaussian distribution, in the case of linear, in the case of regression. In the next lectures, we will focus on different types of tasks, namely classification, where we focus on binary classification or multi-class classification, and we will see what type of distribution do we need for our likelihood to be able to come up with a proper error function. Remember, the application that we need, the types of output that we need. This is why all of this determine the error function that we will have eventually. So from now on, you'll know why they focus on sum squared error function for a regression problem. Some people might just say that that's intuitive. And it is intuitive. That's very understandable. It's sum of differences between the prediction and the actual output. But now you know how, in actuality, they have come up with that squared function, some squared function. So then you'll know that if you were to do a different task other than regression, you will consider that, okay, like this is the output that I would need, right? And this is the distribution I'm going to need for my likelihood because of the task that I'm doing. And then all of this will determine the error function that you will have eventually, right? So the output that you will need will determine the error function. So remember, the outputs and the error functions are tightly related to each other. On behalf of ML Done, take care of yourself and bye-bye.